Hello. Let me share my screen so that I can begin the presentation. Um, this is um this is the presentation on explainable AI and deep transfer learning for Maize disease diagnosis, and it's our final year project proposal, and the authors are Mubarak, Ntanda, Otieno, and Mukisa, and it's being presented by Mubarak. Go to the next page, and the contents of this presentation, we shall look at the introduction. We shall look at the introduction to present to you some of the things that the proposal will cover. We shall look at the problem statement, the related works, the research questions, objectives, methodology, the experimental results that we expect to get. We shall look at the conclusions, the future research directions, and the acknowledgement. Now, on the introduction, now one of the main question that might come up is that why are we looking at maize? Why not any other? Why not any other crop? Now, you should understand that maize is one of the major food crop that is grown mostly in developing countries, and it's the source of so many minerals. Like it has the proteins and vitamins, and it's cheaper, so that means it can be easily accessed by poor people. And for example, in one of the research made by McKee in 2016, it was discovered that in East Africa alone, there was a combined production of about 17.2 million tons. And the maize market actually plays a major role in the well-being of many poor people around not only the East African region, but also the global market, the entire world. Almost everyone consumes maize. It's easier to get, it's cheap, and it has all the minerals that a person would require. Now, if okay, sorry. Now, if if such a food crop is important, then what are some of the challenges that might come in its distribution? What might cause its insecurity? And that's what we are actually looking at. We are looking at some of the problems that affect the maize production, and here we found out that maize production is often affected by various diseases. Now, these diseases are mainly caused by the virus, fungus, and bacteria. But we also found out that maize streak and leaf blight are some of the most significant and widespread maize diseases in the sub-Sahara region, which will be our area of scope. Shall be looking at the East African region, and we found out that maize streak virus and the leaf blight are one of the major diseases that affect. Of course, there are other factors that affect maize production, but maize streak and leaf blight, there are some of the of course we ain't gonna be looking at all of them, but we shall look at maize streak and leaf blight because they are considered as the most important or the significant that affect maize production. And also they cause yield losses and reduction in maize quality and can be difficult to control. So they are considered as a number one priority to farmers and researchers within the region. Now, traditionally, okay, sorry, just a minute. Okay, traditionally, maize disease diagnosis has been relied on expertise in agricultural professions, where people have where farmers to get agricultural experts, which are difficult to find, and take them to his farm. They carry out their tests on the crops. They try to make the diagnosis based on their knowledge and experiments. Now, and experiment all this procedure, the approach, it's not only complex, but it is subjective. It is subjective, and may actually not be accurate because you're using human. They say that human is to error, so that means it involves in a lot of errors, and also the approach can be expensive to small scale farmers. And also we found out that most of the farmers East African region or the sub-Saharan region, local farmers, the people who don't have money, they grow on small scale. And these are the kind of people who can't actually access the agricultural experts. And also there are not many agricultural experts to carry out the tests. So deep learning, deep learning has demonstrated an incredible potential in the area of plant phenotyping. It has been used widely, for example, in monitoring the plant growth and also in testing the soil samples to see the kind of minerals that are in the soil. However, yes, deep learning has showed its potential, but it still has some limitations. For example, here you can see that, yes, we can test, we train an algorithm that can detect that, yes, this is maize leaf blight with an accuracy of 0.93. But then the user or the person can be a researcher or a farmer. He doesn't know how the algorithm came up to that conclusion. He doesn't know when to trust that algorithm or how to correct an error in that algorithm. He doesn't know when the algorithm is correct or wrong and why he should actually trust it. And that brings us to explainable AI. And our goal here will be performance and explainability. Now, the good thing with explainable AI is that you will not only be able to detect, but it will also be able to give you the reasons of why it brought you to that explanation. Now here, the person using the system will be able to understand why the algorithm took him to that conclusion, and also you will be able to understand the evidence that the algorithm is giving him for that conclusion, and he'll be able to make conclusions based on what he has understood from the explainable algorithm. Now here, we should know that we are entering a new age of artificial intelligence, and machine learning is becoming more and more useful. Many people are using it, and for example, here we are presenting it to the agricultural sector. But we should know that machine learning algorithms are opaque, they're non-intuitive. Opaque means that people don't know how they operate, they don't know how the neurons work. They're non-intuitive, meaning that people don't actually understand them. They don't know how they come up to conclusions. So it will be difficult for people to understand such techniques, and yet they are very good at doing what they are doing. Now, explainable AI will create a suite of machine learning techniques that provide more explainable models, while also, so with explainable AI, you produce explainable models that also provide a high level of learning performance. And the good thing with the explainable AI is that you not only provide the explanation, but you can also be able to use the explanation to improve on the performance of your model. And also it will enable human users, like the non-technical people, to trust and effectively manage these emerging technologies in artificial intelligence. So because of this, the goal of this project is provide a practical and effective solution for the diagnosis of maize diseases that can benefit the small farmers and other stakeholders. They can be researchers or other agricultural experts in the maize value chain. And the system should also perform the diagnosis with high accuracy and also provide explanations for its diagnosis. Now, when we come to the problem statement, now we know that maize streak and leaf blight are some of the major threats to maize production, and they've been proven to cause significant losses in yield and posing a risk to food security in the sub-Saharan region now. And also we saw that early and accurate diagnosis of these, actually, when you look at the early and accurate diagnosis of these diseases, it's very important, not only for this disease, but for any other disease. If you're able to detect it early, then it will be easier for you to manage it and prevent the further spread of the diseases. However, accurate diagnosis can be challenging, especially in resource-limited settings. For example, I've seen that these are local farmers. Now, they could see some irregularities in their maize growth, but they don't know what is causing it. So they decide to do what? The own solution will be to call an agricultural expert, which should not only be expensive, but also wouldn't be easy for a person who is growing on small scale. Now, Now, this causes this is really a problem, especially in resource limited settings, where access to specialized diagnostics equipments and trained personnel may be limited. So now this brings us to the research problem, which is to develop a diagnosis system that can accurately diagnose maize streak and leaf blight based on the images of infected plants, and also to provide clear and understandable explanations for its diagnosis. And also we should know that there's been a lack of an effective and easy to use diagnosis system for maize streak and leaf blight diseases. As we have seen, most of them are using trained personnel, which are not only difficult to access but also expensive, and also they lack equipment, making them difficult to use these settings. So the problem statement for this study would be to address the challenges of accurately diagnosing maize streak and leaf blight in resource limited settings, and we shall be using AI and deep transfer learning techniques to develop the diagnosis system that accurately that that accurate and explain and that easy to use. Now there have been some related works in this field. For example, when you look at Coates et al. And his research team used an advanced microscopy technique to study the infection process of E. tertium in maize leaves and its hemibiotrophic behavior. And also, Chen and Wang developed a method for identifying maize leaf diseases using the PNN and image processing with the SVM and artificial neurons. And also, this person developed a method for identifying diseases in corn leaves using adaptive weighted multi-classifier, and he was able to get an accuracy of around 94.71%. Now you can see that these artificial intelligence methods are actually accurate. Most of them that have been used have been very accurate. Now Zhang for him suggested a regularized MTL-CNN, which had an accuracy of about 85.22% with analysis stopping and transfer learning. Now, there are so many others, but based on these studies, we can see that these techniques like, for example, the advanced microscopy and improved deep learning models that have been used, they have high accuracies. They're actually very accurate, but they are not suitable for larger sample sizes or may require complex equipments or extensive hyperparameters. Additionally, some other methods, for example, the SVM, haven't included them in this, but they're in the proposal. They were used, and others like the YOLO architecture have also been used, and they had very good performance, but some of them have also not been compared to see how they perform based on other models. So there is a lack of studies that focus on the explainability and real-time guidance for farmers in the diagnosis and management of these diseases. Therefore, there is a gap in the literature study to develop and compare a range of image classification techniques. For example, that includes both the traditional machine learning and the deep learning. There is a really big gap. People haven't tried to, according to the research we carried out, people haven't used the traditional machine learning techniques and deep learning to try and see which of them performs better than the other. And also, most of these techniques are complex and they're not easy for people to understand, so they will be needing some explanations. And also, in terms of accessibility, most of the techniques used required extensive hyperparameter, extensive technologies to use. So that means we shall be needing equipments that are easily accessible to these small scale farmers. Now, this brings us to the research question. Now, mainly we shall look at traditional ML versus transfer learning. What is the effectiveness of using transfer learning? And also, how does the performance of our traditional machine learning models compare to that of pre-trained models? And also, in the area of explainable AI, we want to know how explainable AI techniques can be used to provide clear and understandable explanations for our diagnosis by the model. How does our model come up to its conclusions? We need to know that. And also we need to know how, because we want to extend these technologies to farmers. We need to know how the use of a mobile application and an external database can improve the usability and accessibility of this diagnosis system. And also we need to know the impact of the diagnosis system on maize cultivation and management of these diseases in smallholder farming communities. Now, this also brings us to the objectives. The main goal of this project is to develop an intelligent system that can not only identify and classify images with maize streak and leaf blight, but also explain how it came up to its predictions and provide real-time guidance to farmers on how to manage these illnesses, and also provide them with solutions or possible solutions to optimize maize cultivation. Now, the specific objectives, we shall need to design an image classification model from scratch that can recognize the presence of maize streak and leaf blight in images of maize plants. And also we shall utilize transfer learning. Specifically, we shall use VGG19 and ResNet 50 as baseline models to design new models and compare the performance of all these models on the task of diagonizing maize streak and leaf blight. Now we shall need to select the best performing model and use explainable AI techniques such as feature importance analysis and salience maps provide a clear and understandable explanation for its diagnosis. Then we shall also need to deploy the explained model on a mobile application and create an external database that will be used to collect and analyze the images from users, mobile phones, as well as a web application, which will work as an interface for the database. Now, this is the visualization, an illustration of the methodology that we shall be using. First of all, after acquiring the data, we shall carry out the exploratory data analysis and pre-processing, where we shall use some of the techniques to analyze the images to see. We shall also see the class imbalances. We shall see whether there are any irrelevant images we don't need in the classes and all that. So specifically, this will be for data cleaning. And also here, after that, we shall after that we shall develop our custom image classification model, and also we shall use transfer learning and VGG19 and ResNet 50 to design two other models. Then after we shall evaluate the performance of these models based on accuracy, precision, recall, F1 score, and the area under the curve. After that, we shall select the best performing models based on these evaluation matrices, and we shall use it for model explainability. Now here we shall use some of the model explainability techniques, like mainly we shall base on feature importance and local interpretability. Now with feature importance, we shall look at what factors the model is relying on to make predictions, and also with the local interpretability, we shall use specific inputs to identify if at all the model is making any biases or not. And specifically here, we shall be using these techniques. There is LIME, there is sharp LRP, and salience map. Now with LIME, or what we call the local interpretable model agonistic explanation, for it is model agonistic, meaning that it can be applied to any machine learning algorithm. And the good thing with this is that LIME will be used to adjust the feature values for a specific, for example, let's say a maize image, and then we track how changing some parts of this image affect the model's performance. Now with a sharp or the sharply additive explanation, it is also model agonistic, meaning that it can be applied to any model irrespective of its architecture. For each it uses the game theory, the Shapley values from the game theory, where it distributes the contributions of different players in a cooperative game. Now here, Sharp will be able to to assign the expected value of each feature contribution, and it will provide us with a better understanding of which factors attributing to the model's performance, for example, in an image. Now, with LRP or the layer-wise relevance propagation, for it, it will involve assigning relevance to relevance scores or values to individual neurons in a neural network, and this will help us to understand which neurons had the most importance on the model's prediction. And there are many others that we shall be looking at. But after providing the explanation to the best performing model, we shall then convert it into a TensorflowJS format. And the good thing with TensorflowJS is that for it, you don't need to host your model anywhere. The person doesn't need to always connect online when he's using the model. So that means when we deploy the model using TensorflowJS, then that means the farmers won't need network every time to scan the images. And that's why we're actually choosing TensorflowJS. And after that, we shall design a web application. This will be designed using Django and React, and we shall host it on Firebase. And the good thing with Firebase is that it comes with its own NoSQL database, and this database will be used, for example, when the farmer scans an image, we shall put an option where he's able to send that image to our repository, because we want to expand on the current database that we have. Sorry, the current data set that we have, because it's about 15,000 images. We want more, we want like million. So the farmer will have an option of sending images to our system. This image will come with other information. For example, it will come with a region, it will come with a date, it will come with current weather. All this information will be recorded on our database, and this we shall be able to view all this on the web application. And also the web application will be able to monitor the different applications that farmers are using and see whether they are facing maybe any difficulties. They should be able to report that, and all that will be interfaced on our admin panel on the web application. Now here on the expected results, we have classification accuracy. We expect to get more accuracy. Now, this is some of the expected results that are visualized. There is accuracy, F1 score, and loss. Now, with accuracy, we expect the model to be more accurate. F1 score, we expect it to be high. The loss should be low, and then precision should be high, and also recall should be a bit high. Now, with the explanations, we expect to get explanations on how each feature within the image was contributed to the model's prediction. So that's what this image is showing. And this was visualized using Sharp. Now it's showing how different features within that image, within that data, contributed to the model's performance. And that's what we shall also aim at obtaining. Then also on the expected results, continuing with the expected results, we expect to get an explanation framework where where we shall be having an explanation model and an explanation interface, where if at all the model is given a task, the user should know how the model came up with the conclusion on that task, on why it came up with that recommendation or decision. And this will help our user make decisions based on the explanation that has been given. Now here, in conclusion, it is expected that the developed intelligent system will be able to accurately diagnose maize streak and leaf blight. And also the use of Explainable will allow for clear understanding of the model's decision-making process. And this will provide us with valuable insights to farmers and agricultural professional experts. And also it is anticipated that the deployment of the Explain model on the mobile application or web application will increase access and usability for farmers, allowing for real-time guidance on these diseases and management. However, it should be also noted that the proposed study has limitations. For example, the performance of the model may be affected by variations in the quality and the resolution of images, and also the effectiveness of the model may be limited by because our data set is small, so the effectiveness of the model may be it is small and it contains only maize images. For example, we don't know what will happen if at all we scan maybe like a cassava image. So the data set is not that diverse. So that is also a limitation. So further research may be necessary to address such limitations. And also on future research directions, we expect to extend the scope of the study to include other types of diseases that affect maize like rust and fusarium wilt. And this would allow the model to be more widely applicable and useful to farmers. And also we shall explore the use of other image classification models or architectures, for example, the autoencoders to see if they outperform the model we've designed. And also we shall consider incorporating additional data sources such as weather or crop management to see how they affect the model's performance. And also we shall evaluate the model's performance on different types of maize plant. For example, shall use it on sweet corn or popcorn to see if at all it generalizes all the maize varieties. And also we shall investigate the potential of using the model to predict crop yield or other relevant agricultural metrics, because currently it will be um, for diseases. So we want to know that it can be used for predicting the yield. And also, we recommend that there should be some feature works on where other researchers can collaborate with agricultural experts or practitioners to understand the needs and challenges faced by farmers when it comes to diagnosing and managing these diseases. And also, they should consider on developing a more user-friendly interface for the model, such as a mobile application. And also, we consider conducting field tests to assess the effectiveness of the model in the real world. And also we consider to explore the potential for integrating the model with existing farming management systems or platforms, because there are some systems that were already developed. So we want to, for example, there is a system specifically at the lab that provides farmers with the information in their local languages. So we would look at integrating such a system. For example, if our mobile application can be used in, for example, Swahili or Uganda, it would be a good thing. Now, acknowledgement, would first and foremost like to send our gratitude to Dr. Joyce, the head of the Makerere Lab, because she gave us permission to work on this project and for her invaluable guidance and support throughout the proposal. Would also like to thank the AI Lab staff, because they helped us in guiding us to the various machine learning areas that we could actually look at and see whether they are more relevant and whether they will impact our project. And also we would like to thank our supervisor, Mr. Galiwango Marvin, for his unwavering dedication and guidance in this proposal, because he used his expertise and support in guiding us on which areas to improve in our proposal. And also would like to thank any other person who has helped us and encouraged us in this project. Yeah, thank you very much. I think that's it. I'll stop sharing.